So we are going to go over the mean value theorem for derivatives. There is a second mean value theorem that we'll look at later in the course for integrals, but this time we're going to focus on how it applies when we're working with derivatives. So to get us started, we started with a warm-up question. That was this. And if you haven't done it yet, maybe you can pause the video and give it a try, and that way it'll mean a little bit more once we take it up. We're going to start with a function f of x equals 5 minus 4 over x, and we're going to do two things. We're going to determine the slope of the secant line that connects points x equals 1 and x equals 4. And then we're going to see if we can find the point between x equals 1 and x equals 4 that has a tangent line with the same slope. So basically in A, I am asking you to find the average rate of change between x equals 1 and x equals 4. And in B, I'm asking you to find the point between 1 and 4 that has the same instantaneous rate of change as the average rate of change that we found in the first part. Okay? So I've written up here the solution that I found, and we'll go through it now. So for part A, we're finding the slope of the secant line, like I said, which is the average rate of change. And I know rate of change is delta y over delta x. So the slope of the secant is the change in y over the change in x. We know that the change in y is going to be the y2 minus y1, or f at 4 minus f at 1. In this case, I found f at 4 to be 4, and I found f at 1 to be 1. So we have 4 minus 1 for our delta y, and our delta x is just going to be 4 minus 1, because those are the 2 points that we're working with. So we have 4 minus 1 over 4 minus 1, which works out to be 1. So I know that the slope of the secant line that connects x equals 1 and x equals 4 is 1. So the average rate of change between x equals 1 and x equals 4 is 1. So what we want to do now is we want to see if we can find a point between x1 and x equals 1 and x equals 4 that has the instantaneous rate of change that is also equal to 1. So remember, when we're working with instantaneous rate of change, we're working with derivatives. The derivative function is a function that allows us to calculate the instantaneous rate of change, or the slope of the tangent line, at any point along our function. So what I did is I took f at x and I found the derivative. So I found f prime at x equals 4x to the negative 2. And this is, like I said, the slope, a formula that allows us to find the slope of the tangent line. And we know that we want our tangent line, or our slope of our tangent line, to be equal to 1. So we want our derivative f prime at x to be equal to 1. Well, we know that f prime at x is equal to 4 over x to the power of 2, and we're going to set that equal to 1. And then all I have to do is just rearrange this and solve for x. I end up with two values that this could be for x. I end up with positive 2 and negative 2. Well, just looking at this solution here, I know that negative x is not on our interval because we're looking between 1 and 4. So the only solution here that works if we're looking between 1 and 4 would be 2. So I know that at x equals 2, the instantaneous rate of change is 1, which is the exact same rate of change as the average rate of change between the two endpoints. And here we just have a little picture so you can actually see what's going on visually. So once again, I have the 2 points that I found. F at 1 is 1, 1. F at 4 was 4, 4. I connected them to find a secant line. I found the slope of that secant line to be 1. And then I found the point at x equals 2, which ended up being the point 2, 3, to have the exact same instantaneous rate of change as the average rate of change between these 2 points. So you can see that the slope of the secant line here is parallel to the slope of the tangent line here. And what we've basically done is we have applied the mean value theorem. So just to be a little bit more specific, the mean value theorem is a theorem that establishes a relationship between, number one, the slope of the secant line that connects two endpoints on a curve, and the slope of a tangent line that is somewhere on the curve between those 2 points. So we want to be able to connect those two things. So basically, the mean value theorem states that if f is a function that is continuous on AB, and that's a closed interval AB. So if it's A is your your endpoint on the left and B is your endpoint on the right, if it's continuous between those two endpoints and also differentiable on the open interval AB, then there is some number, x equals c, between A and B, such that the slope of the tangent at that point, x equals c, is equal to the slope of the secant between the two endpoints that c is located between. Okay? So again, just kind of showing you what we found here. So that basically means that if I have an endpoint at A here and I have an endpoint at B here, and I find the average rate of change between those two endpoints, there's got to be some value of x, we're going to call that value c, between those 2 points that has the exact same instantaneous rate of change as that average rate of change. So the slope of the tangent line here is equal to the slope of the secant line here. So often there will only be one solution here. So this is an example where there's one point between A and B right here at C that has that property. But sometimes it can be more depending on the function. Here's another example. So here I have an endpoint on my left, which is A, an endpoint on my right at x equals B. And I can see in this case, if I take the secant line, the slope or the average rate of change is right here. And there's 2 points on my function that have a similar, or the exact same, I should say, instantaneous rate of change right here at C1 and right here at C2. So it's going to happen at least once, assuming that it's differentiable and continuous, but it could happen more than once as well. So the idea with the mean value theorem is that it allows us now to be able to find these values of C that have that property such that the tangent through them has the same slope as the secant line that connects the endpoints. So that is what we are going to do. We are going to apply the mean value theorem. First of all, we're going to make sure that the mean value theorem applies. And in order to apply, it has to be continuous and it has to be differentiable. So once we have verified that those two things are in fact true, then we can use the properties knowing that there is going to be some point between the endpoints that has the instantaneous rate of change equal to the average rate of change. And we can apply this mean value theorem to help us find what that point is. Now you'll notice here, this is usually the formula that I use. I like to think of it as the instantaneous rate of change being set equal to the average rate of change. But you can also rearrange this. So if I take my b minus a, and I'm just going to hold it together with a bracket, and I multiply both sides by b minus a. Another formula for instantaneous rate of, or for the mean value theorem that says f at b minus f at a is equal to f prime at c times b minus a. So that's this formula rearranged. Okay? So what I want to do is I want to take you through some examples of how we can use the mean value theorem to help us find the value of C between the two endpoints that does have that property with the instantaneous rate of change being equal to the average rate of change. So this is a process that we're going to follow. So this is how to verify the mean value theorem and find that C value between the endpoints. And it's very similar to what we just did in the warm-up. So first of all, we're just going to make sure that the function that we're working with is continuous on the closed interval between the endpoints that we're given. So in order to do this, it helps to have a visual of what that function looks like. So for example, if it's a polynomial function, I know that polynomial functions are continuous because they don't really have any holes or asymptotes or jumps in them. If it's a rational function, I'm going to be a little bit more careful because there's a possibility for things like holes and asymptotes. So I am going to think about my endpoints A and B, think about what that rational function looks like on that interval A, B, and make sure that there aren't in fact any holes or vertical asymptotes where the function might not be continuous, okay? Sometimes it might be helpful to use graphing technology. If it's a function you're not really sure what it looks like, you could use Desmos, plug it in, and just see what it looks like to make sure that it is continuous. But usually you can do this just by analyzing what the algebraic representation looks like. Once we've done that, so once we've got our check there that it's continuous on the closed interval AB, you want to make sure that the function is also differentiable on the open interval a comma b. There should be a comma there. So basically, you're looking to make sure that you can actually find the derivative and that the derivative exists for the original function between a and b. So you're going to find the derivative, find f prime at x, and then just make sure that there's no places where it doesn't exist on the interval that you're looking at. Okay? So once you've determined that it's continuous, check, and it's differentiable on the open interval, check, then you can go ahead and see if you can find that value of x, and we call that value of xc, where the instantaneous rate of change is equal to the secant slope of the endpoints. So in order to do that, what we're going to do is, because we're looking at instantaneous rate of change, we're going to find the derivative of f at x. We're going to calculate the average rate of change between the endpoints. So we know that's f at b minus f at a over b minus a. We're going to sub c into our derivative so that we can solve the equation f prime at c equals f at b minus f at a over b minus a. And once we've solved that equation, we should find some values of c. And we always want to make sure that our values of c are in fact on the interval that we're looking at between a and b. So you're going to check your answers and just verify that they are actually on the open interval that we're looking at. And if it's not on the open interval, then we just exclude it from our final answer. Okay? So I'm going to take you through a couple examples of the mean value theorem and applying the mean value theorem. And what I would like you to do is just take a minute, try the question, and so pause the video, try the question, and then we'll go over the solution together. So the first question says, for each of the following, determine, first of all, whether the hypothesis of the mean value theorem is satisfied. And if it is satisfied, find C. And if it's not satisfied, then just tell why. So our first function that we're going to look at is a quadratic function. F at x equals 3x squared minus 6x plus 1. And we are going to focus on the interval, the closed interval between -1 and 2. So here's a little checklist. So what we want to do is we want to think to ourselves, first of all, is this continuous on the closed interval AB? Is it differentiable on the open interval AB? And then if these two things are true, then we can go ahead, we can figure out what the slope of the secant is between the endpoints, we can find the derivative, sub and C for the derivative, and find the value that works for the mean value theorem, and then just verify that's on the interval. So take a minute, pause the video, give it a try, and come back to see how you did. Okay, so here is my solution to this problem. So first of all, is this continuous on AB? And I know that this will be shaped like a parabola. It's a quadratic function, f at x. And I know that f at x and parabolas are always going to be continuous between negative infinity and infinity, in fact. So because this is a polynomial function, I know that f at x is going to be continuous. So I'm going to check off that it does satisfy the condition that it is continuous on the closed interval between -1 and 2. And then I'm just going to find the derivative. So the derivative of this, f prime at x is equal to 6x minus 6. And again, I know that this polynomial function, is going to be differentiable on that interval as well. So second condition that is differentiable on the open interval, -1, 2 works as well. So I can check off that this function has met those two conditions. And therefore, I can apply the mean value theorem to help me find the value between -1 and 2 that will have the same instantaneous rate of change as that secant line slope. So I'm going to first of all figure out what the slope of the secant is. So I have delta y over delta x, which is f at 2 minus f at -1 over 2 minus -1. I end up getting -3 for my slope of my secant, or my average rate of change. And I know that my derivative is 6x minus 6, or 6 times x minus 1. So what I'm going to do is I'm going to sub in c for my x. So that means that, so up here, I'm going to sub in c right here. So I'm going to have 6c minus 6. So I know that 6c minus 6 must equal the slope of my secant, which is -3. And now all I have to do is just solve for the c value that makes this true. So I end up rearranging this to get c is equal to 1/2. And 1/2, luckily, is on the interval between -1 and 2. So we are good to go. We know that at x equals 1/2, the slope of the tangent line will be -3, and that will be the same as the slope of the secant line that connects those two endpoints. Okay, so the mean value theorem applied, and then we were able to find the c value for x that has the same instantaneous rate of change as the average rate of change. So here's our next question. So same thing, this time we have a rational function, f of x is equal to 1 over x minus 2. And hopefully you can look at this function and have a little bit of an idea of what it might look like based on your knowledge from other courses you might have taken. And we are going to see if the mean value theorem applies on the interval from 1 to 5. So first of all, we want to see if it's continuous on AB. Is it continuous or differentiable on open interval AB? And then we can apply the mean value theorem to help us find that c value if, in fact, the mean value theorem will apply. So again, I want you to pause the video, try this question, and then come back for the solution. Okay, I know this is a rational function, and when I look at the denominator, it is clear to me that if I sub in x equals 2, I'm going to have 1 over 0, which I can't have. I know that there's actually going to be a vertical asymptote at x equals 2. So, and the number x equals 2 is on this interval between 1 and 5. So right off the bat, I know that this function is not continuous on the interval 1 to 5. So the mean value theorem does not work, and I stop the question because it's not continuous. I cannot do any more work with this. I cannot find a point C that has the average rate of, same as the average rate of change. So I'm going to move on to the next question, knowing that because the mean value theorem conditions did not apply here, I cannot actually do the work. Okay, here's another one. This time we have f of x equals x to the power of 1 over 3. And we're going to look at this on the closed interval between -1 and 3. I threw this into Desmos just so that we can have a little visual of what's going on here. So this is what the function looks like. And we're looking at from -1, which is kind of around here, to, sorry, -1 is right here, to 3, which is over here. So we, again, want to make sure that the conditions of the mean value theorem apply, and then if they do, we can find that point C. So pause your video, take a second, try this question, and then come back to see a solution. Okay, so looking at this graph right here, I can see that this function is in fact continuous on the closed interval between -1 and 3. So the first condition is a check. That works. It is continuous. However, when I look at this function right here, I see a perfectly vertical point right here. And I know that if I have this shape, that this is going to be a spot where I am not able to differentiate the function. So just to prove that, I'm going to show you what I did. So I saw that it's continuous, but when I calculated the derivative of this function, I end up with 1/3 x to the -2 over 3, which is the same as 1 over 3 and then the cubed root of x squared. So those two things are equivalent to each other. And this helps me visualize a little bit because I know that if I have a fraction, the denominator can't equal 0. And if I sub in x equals 0, then this function is not a real, the y value will not be a real number at this point. So there is a restriction on this derivative that x cannot equal 0. So that tells me, as I suspected from the visual right here, that this function is not differentiable at the point x equals 0. And x equals 0 is on the open interval that we're looking at, -1 and 3. So even though it's continuous, the original function was continuous, because I can't take the derivative of it at x equals 0, then it's not differentiable on our interval. The mean value theorem is not satisfied, and I just have to move on. I can't do anything else to this to be able to use the mean value theorem in order to find that value between the two endpoints that would satisfy the mean value theorem. So this is another example of where the conditions of the mean value theorem weren't satisfied, so that I can't actually do the question. Okay, and I've got one more here. This time I've got the function f at x equals the square root of x, and we're looking at it on the interval between closed interval from 0 to 4. And hopefully you have a little visual of what this graph looks like in your head, what the square root function looks like. So pause the video and see if you can figure out the value of c that works for this. Okay, so here is what I get. I have here that I know on the interval between 0 and 4, I know that it's going to start at 0, it's going to go to the right, and that it's going to be continuous on that closed interval. So we are good to go there. In terms of differentiability, I am going to take the derivative of this. So I get f prime at x equals 1/2 x to the negative 1/2, which is 1 over 2 square root of x. And I can see that this derivative doesn't work when I plug in x equals 0, which is on one of my endpoints. However, differentiability is connected to an open interval, not a closed interval. So even though I can't use 0 in this derivative, everything above 0 I can. So because it is an open interval, it is in fact differentiable on this open interval, and I'm good to go. Okay, so it does satisfy those two conditions of the mean value theorem because it's continuous on the closed interval and differentiable on the open interval. That 0 is not included in the open interval requirement for the mean value theorem. So I am going to plug in my value of c into my derivative. So I'm going to have 1 over 2 square root c. So I've plugged that in here for my f prime at c. And I'm going to calculate the slope of the secant. So I have f at 4 minus f at 0 over 4 minus 0. So I end up getting 1 over 2 root c equals 1/2. And I just flip them both around, or I cross multiply, however you want to think about it. And when I isolate for c, I get the square root of c is equal to 1. If I square both sides, that means that c is equal to 1 as well. And it works out because x equals 1 is on our interval between 0 and 4. So that means then that at x equals 1, then the slope of the instantaneous rate of change at x equals 1 is going to be exact same or equal to 1/2, just like the average rate of change between 0 and 4 for this particular function. So the mean value theorem, I was able to apply it, and then I was actually able to do some algebra to figure out that value of c or x that works for this situation. So hopefully these examples kind of help you out a little bit and give you an idea of, first of all, how to tell if something is continuous and differentiable. And again, a lot of that just comes from our knowledge of functions and what they look like and their behavior. And then how to then use the derivative and use your average rate of change between the endpoints to help us find that point on the interval that has the instantaneous rate of change that is equal to the average rate of change.